Thanks very much, Manuel. So yes, welcome to the lambda calculus session. I'm going to be describing some work mostly done by my first author here, Chun Tian, who is unfortunately in Australia not able to get the appropriate sorts of visas to come here. So I hope I do, as I said, what is mostly his work justice. Basically, the whole point of this exercise is to take this classic text from 1984 and 600 pages and turn it into formal mathematics. I mean, when I say slow motion, I really do mean slow motion. The original piece of work I did on this was from about 2009 or 10, and it has sat pretty much unchanged since then. But luckily, when Chun arrived in Australia, he agreed that we should do some more on this front. And so that's kind of this paper is the outcome of all the work that he did. So because we wanted to mechanize this, most of the proofs have come from this. We have varied some of them slightly. And there's a few places where, in particular, some of the proofs by Takahashi, who has this beautiful paper about lots of results to do with confluence and standardization and eta contraction in a paper from probably 10 years after this book came out. So we used some of hers. The title of the text is The Lambda Calculus, but in fact, as people may appreciate, it's very much the untyped lambda calculus. Barendrecht has a separate book on the typed lambda calculus, but this stuff is very much in the world of Y combinators, and types are for other people. And in the earlier work that I mentioned, I proved things like standardization and finiteness of developments, and Church-Rosser, of course. That stuff certainly was required as a prerequisite for what I'm going to describe today. The untyped lambda calculus looks like this. We have a set of lambda terms where you have variables. Now, if I can, is my mouse visible on the screen? So I don't have a laser pointer, but I do have the ability to wiggle. So you can either have variables, abstractions, or applications. So those are the three constructors, as you might think. But we also have alpha conversion. Now on this slide, I'm using Barendrecht's notation. So the triple equals, the equivalence here is syntactic equality. So lambda x dot m is syntactically equal to lambda y dot m, where you've replaced the x with the y. So lambda x dot x is equivalent. Well, you tend to think, oh, that means equivalent, but actually means syntactically equal to lambda y dot y. So then Barendrecht uses equals to actually mean this theory. So he develops a proof system for lambda calculus equality, where he says that lambda x dot m, so this is the very first rule of the theory, right? Beta reduction or beta conversion, right? These two terms are equated in the theory. The theory is reflexive and symmetric and transitive. Those are the next three rules. And then it's a congruence with respect to application, so on the left and the right. And it's also, you have equality, the abstraction is also, equality is congruence with respect to abstraction. So this is the theory of bold lambda. I hope it's obvious that this is this bold lambda, and it's a proof system. And then we can add to that proof system with eta, where we throw in this extra equation that says that lambda x dot mx is equal to m, as long as x is not free in M. So that's an additional rule that you can choose to add. And if you add this new axiom, if you like, you get the lambda eta theory. And then we can talk about what it is to be provable. And so we have lambda turnstile m is equal to n, or sometimes just m is beta equal to n. And then provability in the extended logic is you put the lambda eta on the left of the turnstile, or you put equals to the subscript beta equal n. So now the beauty of this setup is that we can then talk about adding extra assumptions, or axioms if you like. So we can talk about lambda plus p equals q, is that with extended by the equation p equals q. And so, for example, in lambda plus p equals q, you could prove lambda x dot p is equal to lambda x dot q by taking this as an assumption and then using this rule over here that allows you to wrap equations with abstractions. So that's the basic machinery of the logical system. I'm probably not going to use the triple equals very much, but here and on the next slide, I'm still not yet in the world of whole where I did the mechanization. So the other important vocabulary is this notion of consistency. So the theory is not useless, means that it doesn't prove every possible equation. So it's consistent if we allow that. So this is very easy to prove, and it's a very standard result that lots of people prove in the theorem proving system of their choice when they first encounter the theorem proving system of their choice. because it's a fun exercise, and it follows from Church-Rosser, because if two normal forms like S and K were equal, then they had a common reduct. So you imagine the little confluence diamond, and if S were equal to K, they must be able to reduce to a common point. But in fact, of course, they can't reduce any further because they are in normal form, and so that would mean that S was syntactically equal to K, and we know that's not the case. So indeed, Church-Rosser for this equational theory demonstrates that the theory is consistent, right? Because S equals K is not a member of the equational theory. And the same sort of proof argument works just the same for lambda eta. So those systems are consistent, and as Beniamino Akitoli, I think is the right way to say his name, author of the next paper, observed in one of his papers, this has been mechanized countless times over the last sort of 40 years, but people tend to then stop. And the next property is one that hasn't been proved until our work, we believe, mechanically. And this is completeness. So I quite like the equational theory is full characterization of what this means. It says that if M and M have beta eta normal forms, then either that's already a theorem of your system, so here, or adding it would break the system. Okay, so if you like, you can read this as saying lambda eta plus M equals N is inconsistent, could be read as M is not equal to N. And then it's basically theory completeness in the sense that Gödel uses completeness. We're talking about arithmetic being complete. Either it's true, either you can prove that it's true or you can prove that it's false. Now, we can't prove things false, strictly speaking, in this equational theory, but we can observe that assuming something would lead to an inconsistent theory. It's not quite the same. This result, in turn, follows from a result from 1968 that is then written up by Barendrecht, and that hasn't been formalized either, and I'll tell you why in a minute, but the short version is because it's a pain. So we have the outline of what I'm going to tell you about today is that we have successfully formalized the lambda eta completeness result from that slide, mostly following Barendrecht. Böhm's separability theorem in its full form we have not yet completely finished. I'll explain the nuance there, but with a restricted version of that theorem we could still get the completeness result, and it was the completeness result that we saw as our principal objective. So as I say, we have a slightly novel proof there. These proofs all involve this notion of Böhm tree. Strictly speaking, Böhm's original paper doesn't actually talk about Böhm trees, but by the time Barendrecht came to write it up in 1984, the community had obviously figured out that these things were trees. In 1984, they didn't see them as co-inductive. That language hadn't sort of obviously taken hold. But if you look at Barendrecht's much more recent book from about a few years ago, indeed there, Barendrecht observes that it's a co-algebraic structure. And we do not quotient our Böhm trees with respect to alpha equivalence. And so, in fact, we have to deal with names in a fairly arduous fashion, which I'll also talk about. Right, so whole 4 is the system that we use to do all of this work. And so the existing, that's the work I told, no, it's in 2006, my goodness. Okay, it was a long time ago. So that provided 3 constructors, a type that looked as if it had 3 algebraic constructors, var of x, lam x of t, and t applied to t prime or app. The variables are all just strings, so it's completely concrete, but the type is nominal. So we do have, and now this is a whole equation, this is not lambda theory, not the equality of the equational theory, but just whole syntactic equality. So it is the case that lam x var x is equal to lam y var y, right? And that's because there has been a quotient performed on the underlying raw syntax type. And so, and that theory in turn follows as a consequence of this more general result that says any 2 abstractions are equal if the 2 bound variables are the same and the 2 bodies are the same, or, I hope you're parsing this formula as well as I am, that's that clause, or they're not equal, and I'll explain this in a second, but u is fresh for, u does not appear in the free variables of t2, and t1 is equal to the permutation, in the nominal sense, of u for v inside t2. So that captures the definition from over here. Y is not free or bound in M, so that's syntactic identity. Right. And then, as I said, we have this x sharp M syntax for not being in the free variables of M. We have a constant called free variables. And then the result of doing a substitution, this is my favorite textbook notation, but unfortunately, certainly in 2006 and maybe even now, that notation would have been hard to achieve in hole 4. So we use this kind of slightly weird n for x applied to m notation. So Barendrecht's English or mathematical prose formulation of this famous substitution lemma, it looks like this, and immediately underneath it is the hole 4 version where, I mean, so I've literally printed this into the slide from hole 4. So this is L for y, n for x, O into m is equal to this complicated thing where the substitution moves in over the other substitution. And then in one or two places, you may see this I sub infix. So M I sub with a list of substitutions is literally just perform a whole bunch of substitutions, one after the other. So it's not simultaneous substitution. Right. So the other important notion that we're going to use is head reduction. So head reduction is a subset of beta reduction. And it says, well, if you're looking at a beta term, you can reduce it. You can reduce under an abstraction, and you can reduce to the left of an application as long as the M1 term that you're reducing in is not itself an abstraction, because if it were, you should be using this rule. So that's head reduction, just 3 rules. And then this uniquely determines for any given term a head reduction path, right? Because there's only ever one place where you can perform a head reduction, and so you get this unique path. The path may be infinite, and so it's a co-algebraic structure itself. And then a term is in head normal form if it looks like this, where you have a vector of, possibly empty vector of bound variables on top of a variable applied to a bunch of terms that may be of any flavor. So this is in head normal form. So we say that a term has a head normal form if it's beta equivalent, i.e. can reduce to a head normal form. And in fact, there's a nice result. This is pre-existing work that the term has a head normal form if and only if its head reduction path is finite. And then we will occasionally see this double arrow notation for the reflexive and transitive closure. So take many steps along that head reduction path. Okay, so then we have this notion of principal head normal form. So if you, the same term, because you can reduce in places that are not important, may end up having multiple head normal forms because you're in head normal form, but so you look like this, but the m's here might be doing all sorts of weird reductions independently of each other. And so you have multiple forms that are head normal forms. But the so-called principal head normal form is where you just do the head reductions and you don't let yourself be distracted by any other reductions that might be hanging around to the side. And so the definition is literally the principal head normal form of a term is equal to the last element of the head reduction path. Now, the head reduction path may be infinite, in which case this has an unspecified value. It's akin to dividing by 0. But if it exists, we get lots of nice properties. So if something has a head normal form, then it will reduce to its principal head normal form, and indeed its principal head normal form is in head normal form. That's the first theorem there. The set of free variables of a principal head normal form are always a subset of the originals. Again, that's true for beta reduction in general. And then this last one is a bit curious. It says if T is a head normal form, then if we wrap a whole bunch of variables around it and then apply the result to the same variables, so map is just is like mapping over with lists. So if we apply those same variables to this, we will get out T. And I will try to explain as we go on why that result is actually particularly important. And the very last little bit of tangential work I want to talk about is the notion of solvability. And so a term is solvable if you can apply it to a bunch of arguments and get out the identity term, right? I here, lambda x dot x. So an arbitrary, so that's true for a closed term, and then it's a term with free variables is solvable if you close it up with a bunch of abstractions to get rid of the free variables and then apply it. And so the definitions, I hope you can see captured that. An example of an unsolvable term is the famous omega, which will just constantly sit looping. And so omega is just lambda x var x applied to var x, lam x applied to var x. That is unsolvable, but there's a famous result due to Wadsworth that says the lambda term is solvable if and only it has a head normal form, which is a very curious result. It's not immediately apparent, I would say, but it turns out to be the case. And I am pleased to say that 2 people first mechanized this result, because in fact, immediately after me, Adrienne will be talking about her mechanization with her co-authors of exactly the same result, among other things. Right, so Böhm trees, I promised you these. So if a term is unsolvable, then we say that its Böhm tree is the bottom value. Otherwise, if it's not unsolvable, then it has a principal head normal form. And then we say that the root of the tree is then just the vector of the bound variables and the y. So we kind of just focus our attention on this, and we say that's what's sitting at the root of the corresponding Böhm tree. And the subtrees are the Böhm trees of these m0 through mn-1. So if we take the S combinator, which is lambda ABC, AC, BC, then the root is just, as I said, this component, the lambda ABC and the A. And then underneath, we read off the remaining terms, which is the C, and then the B and the C. Now, the C sits here on its own because it's just a variable, but B applied to C is itself got to be reduced to a Böhm tree. So it will look like, well, there's no bound variables, so it's just, there's no lambdas, but there's a B, and then underneath it is the term C. Okay, so that's a nice finite tree corresponding to something that's in beta normal form. If you use omega and stick it into your term, then you unsurprisingly get a little bottom hanging around corresponding to that omega. So that is, so it's lambda c dot AC omega. So here's lambda c and A, and then the C is the first of the children after the head variable, and then the next thing is just bottom. So we can also, and this is where you need the co-algebraic nature, have an infinite Böhm tree, for example, y here. Now this is correct, if you like, because we know that y, as per this footnote, y is equal to, y of f is f of y of f. So indeed, y is going to be a lambda term where the head variable is f, as per this, but then the first child is going to be exactly the f, etc., all the way down. And so we have an infinite Böhm tree. Okay, so far this is just the informal presentation of Böhm trees as you would find it in Barendrecht. One thing Barendrecht says about this world is that he thinks the best way of dealing with them would be to use de Bruijn indices, because dealing with the alpha equivalents of these structures is tricky. So we don't use indices, we use free names and a first order structure. So we do not attempt to do a quotient, but this causes all sorts of problems with finding free names on demand that will keep everything suitably fresh. And so look at the bottom of the slide, I guess, to start with, and think, I am going to allocate strings in rows. So I have a two-dimensional arrangement of all the strings in the world, because we know that strings are of equal cardinality to the natural numbers, and the natural numbers can be put into pairs. And so when we call alloc, we allocate a bunch of names starting on row R, starting at Z, and we want n of them. So it's very important to be able to do this two-dimensional allocation to give us principles that work well with inductions and co-inductions. But I don't think I want to belabor this, but we are going to do lots of allocations in this flavor. In particular, if we want to avoid a finite set of strings, x here, then we figure out where we want to sit off to that blob's right. And because it's finite, there always will be a maximum column past which this set of strings does not extend. And so if we want to allocate on R, we can always find a position. And so you'll see a few instances of this R news constant in the remaining theorems, and its definition is basically guaranteed to ensure that you can get n fresh names, all of which share this property of being at row R in this 2D matrix, and avoiding x, as long as x is finite. And then finally, we have this rank less than R, which is just all the names that sit below, in the rows less than R. Right. So that technology is super useful, and here is the first critically complicated definition to try and get your head around. This is how do you generate the Böhm tree formally in whole 4 given a particular argument m. Now, you'll quickly say, well, what about the x and the r? So the X gives us the ability to say, we want a Böhm tree, but don't ever mention the set X. And the R says, we want to start our names at level R. And in particular, we're going to recurse on that R. So the first thing you need to do is figure out what the principal head normal form of M is, right? So you can see this big let. Well, so first of all, there's the test that says, are you solvable or not? If you're not solvable, then you're bottom, which corresponds to this none. If you are solvable, then you generate the principal head normal form. Now, then you figure out how many abstractions are sitting in the principal head normal form. So M0 is of the form lam, so lamel takes a vector of names. So n is the length of that vector of names. And then there's a y, a distinguished variable y at the head, and then there's a bunch of children m's. So we then allocate some fresh names. So at row r, which has been passed in as a parameter, avoiding x. So we're guaranteed to be safe in that respect. And then m1, of course, we take the principal head normal form of m0 applied to those variables, and those variables will cancel out the abstractions. And so now we have a term, after we calculate the principal head normal form, now we have a term that is just an application of, because we've effectively scrubbed this lamel, we effectively have a term that looks like variable y ... m's, or something alpha equivalent to that. So then we can count the number of children, or get the children, sorry, the m's here. We can get the head variable, which is going to be, well, it may not be y, because of course that variable y is not necessarily free with respect to v's in the principal head normal form. So it may in fact be different by now. And then we can repeatedly, effectively recursively call ourselves on all of the m's. And we'll notice that the only thing we do there is that we increment the rank. So the names associated with the head normal form at the top of the tree may be starting at R, and then in the next level down, all the names will be at R+1, and then R+2, R+3, etc. And again, that sort of inductive characterization of the names we're going to be using, we're using effectively canonical names rather than equivalence classes. And so we need to be able to allocate our canonical names in a clean way. And then our data structure represents the information at that node of the tree. In the pictorial version of the tree, I wrote lambda abc.a, for example, for the S combinator. Here we would just write the list ABC and the singleton A, or none if it's bottom. So that then is a hard-won definition, and the use of the ranks is very important because it lets us do inductions. So here is a corresponding one that looks very similar, so I'm not going to step through it in quite the same way, but it's talking about, given a term, M, again, and a free set X and a rank R, follow the path, which is the third parameter here, and give me the term at that position in the Böhm tree. So the index is I constant i's is just a list of numbers. If it's solvable, you do the same sort of thing. You generate the principal head normal form, you smash in the canonical set of free names, you get the children, and then you index into the list of children by doing this. And then you can repeat, so you can call subterm x li m's of i's, where i's is the tail of the list from up here. Otherwise you say, well, there's no such subterm. So we can prove that, and this is one of Barondrek's results, that if you have a position in M that's not none, then if you look up in the tree along that path, that's the same as computing the Böhm tree of the subterm of that path. So, I mean, it's saying something that's actually quite obvious, but was relatively difficult to prove. Right, I should get a move on. So the basic properties of the Böhm trees are that two beta equivalent terms have the same Böhm tree. If a term is in beta normal form, its Böhm tree is finite, and the free variables of a Böhm tree are in this shape where the free variables of a child are a subset of X union rank suc of R here, so successor of R, so R+1. Then we need to talk about the notion of a Böhm transformation and the Böhm outs technique, and we need to be able to apply a Böhm transformation to a tree. And a Böhm transformation is a sequence of operations that's either adding a variable onto the end of the term, or performing a substitution. And it's a congruence with respect to the equality. And then you can construct a Böhm transformation that takes the tree and smashes it in such a way that you end up with something that is ready. And ready means that you are in a fantastic position and able to do a reduction on it. So if a ready term is solvable and of the shape, has a variable at the head, and that variable doesn't appear anywhere else. So two Böhm tree nodes are head equivalent by looking at this pattern of the variables and the body of the single node. So without ignoring the structure of the children, then we say, well, they've got the same variable y, and either they've got the same number of bound variables and the same number of children, or the number of variables plus the number of children, no, sorry, the difference between the number of variables and the number of children is the same, which means that we could add extra variables to the shorter of the one, and then we would get, we would continue to be equivalent because we'd be adding abstractions and adding variables, which is effectively eta expansion. And so the Böhm out technique, and this is the killer theorem that allows the final result. Again, gosh, I am running out of time. So this says that not only can we do that transformation for a single term, we can actually do it for an arbitrary list of terms, which means that the Böhm transformation that we get for any list of terms pi here makes everything ready and able to be eta converted. So then we finally get Böhm's original separability theorem modulo a slight restriction that says if you have two terms m and n, when you transform them, you can transform them in the way to generate p, an arbitrary p, right? For any possible term p, you can apply the transformation to m and you get p, and you can apply the transformation to n to get q. Right, so finally, I can show you the proof of lambda eta completeness by separability. So this is the eta separability made pleasant. If I have two terms that are not beta eta equivalent but do have normal forms, then I can apply the pi to both and get p on one side and q on the other. And so if I have a p and a q and they're not equal, then I want to show that assuming them equal would lead to a contradiction. And I do that by applying the transformation to each and get my arbitrary p and my arbitrary q. And that would allow me to demonstrate a contradiction. So the only restriction is that Böhm's original theorem allows me to keep, you know what, I might skip past that in the interest of time. We can eta expand terms in a way to do it. And let me conclude by saying that we finished by proving this lovely famous result due to Barron-Direct, and we have this nice technology for working with the Böhm trees. And I hope that we'll be able to take this and use it to mechanize other Böhm tree-like structures. And then they can be also the basis for the sort of denotational semantic models of the lambda calculus like D infinity. And then there are some polishing steps to be done. Having proved Barron-Direct's final result about the Hilbert post-completeness, there's tweaks and things that we would like to also do. And sorry for going long.